So in this class, we are going to have our continuation of the DC motors, now considering the series wound motor. If you refer back to the series generator that we had, you are only going to notice the difference that this time we are working with a motor. So what a motor does, it draws in the current. A generator was supplying the current like this to the load. But what is going to happen with the motor is that it is going to be drawing in, it is going to be taking in the current. The combination that we had is not going to change, guys. Everything that we had is not going to change in terms of the simplification of the series. And noting that it's a motor, so always when dealing with a motor, we do understand that the input is electrical. Input is electrical. So we talk of the voltage times current there, where the output now is mechanical. And because of the difficult challenges of calculating the mechanical power, we're going to just leave it like that. Note that that is what we have at the output. Meaning to say at the input, as we are to consider where the terminal voltage is, we are going to be having the input power. This is our load current. To the series field, where we have got the series resistance as we had before, the current is flowing into, take note, into like this. So meaning to say we're going to have the current in the series field, that one which is going to flow into the armature, referred as our armature current, that's having the generated EMF, which is the one that we call the back EMF, as you are to consider a motor, and the output, which is the mechanical, as you are to consider having that rotation due to the torque that we talked about before. Remember, this is a rotating armature. A rotating armature where we are going to also consider its armature resistance. We had this diagram, the only changes that we are seeing, current and the power. That is the only part that has changed. That's the only part that has changed. So on our calculations, we are going to notice in terms of the currents, still have the same thing because the series. So these currents are the same. So that is the load current is equivalent to the series field current is equal to the current that is flowing in the armature. And as I said, the input power is electrical. So therefore it can be calculated from the terminal voltage times the current, but the current that you are referring is the load current, where the output power is what? A mechanical power that we cannot calculate. Just leave it like that for now. We also need the generated EMF. As I stated in the previous class, when we are talking about the EMF equation of a motor, remember I said that the EMF equation can be calculated from E is equal to V minus, we're dealing with the motor, the back EMF, armature current times the resistance of the armature circuit. This is the basic formula that you need, where the resistance of the armature circuit has to be considered according to your diagram now, where the armature current is flowing. If we check according to this diagram, all this part is going to be affected by the armature current because it is a series combination and the current is the same. So where the armature current is, there is a series, there's also the resistance of the armature. So this formula, therefore, can be made an adjustment on it, meaning to say it's going to be V is equal to the armature current into what? The resistance of the armature circuit. We're talking about the resistance that is on the armature and that resistance of what? The series field, like that. So that will be your formula that you need. Like I said, your power output is mechanical. So with this, guys, as you can see, that is the only adjustment that we have from the generator. So nothing has changed there. On this example, we're given that a DC series motor, it's a series motor that you're given there. So the moment that you're given a series, that know that combination of your series, having your armature as we had before to the what? To the terminals. So they're saying there, it's a DC motor, take note. So meaning to say it's going to be taking in current. Here's a back EMF. They gave us the back EMF on this one of 220 volts. So the back EMF, 220 volts. Induced in its armature, which has a resistance of in its armature, which has a resistance of in its armature. So you're given the resistance of the armature there, of the armature circuit, of the armature part here, of the armature only. We're given the resistance of the armature there, 0.22 ohm. If the motor takes, meaning to say from what? From the supply, it is taking in, like I said, a motor, it takes in. So that is the load current that you're given, 35 amperes. From what? 250 volt supply, which is our terminal voltage. Calculate the resistance of the series field. You do not know the resistance of the series field here. So what can we do? We have this formula as we had in a series. So we can consider to say from our EMF, the generated EMF, the back EMF that we are given there, what can we do? Because we are given that back EMF. So we saw that from the back EMF, E is equal to what? That's V minus armature current into what? We ended up with RA plus RSE in a series. So this is what we need, of which if you were just to expand the brackets, it's going to be V minus, we are going to, you can make the subject as it is like this. As it is like this, or you can expand the brackets by the armature current, so it will be minus armature current times resistance, you minus this multiplies there, so it's a minus again, armature current times the resistance of what? The series field, which is the one that you need here. So the part that we need, it's a product and it is carrying a negative. So let's just avoid it here being a negative. Let's take it to the other side of the equation so that it becomes a positive there. So it's going to be armature current times the series field is equal to what? We have taken this as it is, this part. It has crossed the equal sign, so it becomes a positive. So meaning to say you are going to remain with what? This side. You are going to remain with this part, which is V minus armature current times the resistance of the armature. Then we take the E to the other side. The moment it crosses the equal sign, it will be a negative there. So that's where we are, and we need this. So what are we going to do? Simply divide by what? Armature current. So by dividing by the armature current both sides like this, you are left with what? The resistance of what? Of the series field. So that was the condition that we are going to have. So it was just a matter of substituting now. Are we having this? Remember, it's a series. As we consider that in a series, these currents are the same. The load current is equal to the series field, is equal to the armature current, as I stated before. So as we are given this load current, we are also given the armature current. So everything is there. It's just a matter of substituting. What is our V? The terminal voltage, 250 minus the product of armature current, which is same as what? Which is same as the load current there. Just going to use the load current that we're given. That is 35 times what? The resistance that you're given of the armature, which is 0.22, minus the generated EMF or back EMF of 220 volts, everything over what? Armature current, which is your load current as it is the way that we used it before, which is 35 amps. that was going to give us the resistance of the series field. And this resistance was going to be 0.637 ohms. We have the resistance. So adjustments can be made. So make sure you draw your diagram properly, everything being inserted. If you check this other example that you're given, they're also saying it's a series machine. And they did not specify to say, is it a motor or is it a generator? That they are saying a series machine draws 35 amperes from this supply. It draws current. The one that draws current is what? The motor. So they are specifying in a hidden manner that this is what? This is a motor. A motor draws in current. Whereas if it is a generator, it what? Supplies. A generator, it supplies current. So be careful about that. So we know that this one is a motor because of that information. And it's a series machine. So they are saying it's a series motor. That is what they are saying. It's a series machine which draws in current. So they are saying it's a series what? It's a series motor which draws in. The current is taken from the supply entering, which is the load current is given as 36 amperes. From the supply, from this 340 DC supply, which is our terminal voltage. The resistances of the armature and series field respectively, meaning to say they gave us first, the first one of the armature, 0.25. And of the series field, 0.3. With this time you're given these resistances. So from this information, calculate the machine's constant. All right, remember this is the rotation there. The machine's constant. Okay, so they want you to calculate the machine's constant if it operates at a speed of 980 revs per minute, and the useful flux per pole is. All right, what an interesting question. Let's see what you're given there. 28.75 milliwebs. They want you to calculate the machine's constant. All right, so the question that you're going to ask yourself is, what is it that you refer to as the machine's constant? The machine's constant is taken from the generated EMF, from our EMF equation. Remember, from our EMF equation, this is what we do understand. We understand that it is two flux like this, NPZ like this one over 60C. And from this one, we have a constant from the concept that 2 that we are seeing is a constant. The 60 that we are seeing is a constant. The pair poles that we are seeing is a constant. The Z number of armature conductor is a constant. Also, the 60 here is a constant. These are constants. So, meaning to say, they are to be taken to be a single constant, all these. The 2, the P, the Z, they are to be taken to be a single constant as they are. So it's going to be 2 on top. There we've got P, there we've got a Z. Everything over 60C. Like this, it is the machine's constant like this. But do we have all this? Are we given an information that further tells us about this? No. The P, remember, is the pair poles, and we are not even told about the pairs there. The number of armature conductors, we're not even told. Even to say it's wave or it's lap, we are not told. So the formula here was going to limit us. This formula. So what are we going to do? let's take the K and use it back here and say E is equal to, because we have removed all these constants that we have, all these constants, what is remaining if you remove all these constants? Because it's now a single constant, which is written as a K like this. I want you to see what is remaining. There is flux there, and there's also N. These two are remaining after you have removed these. So you're just going to substitute because you're going to take this, replace all these, the 2, the P with what? With a single K. That's your machine's constant. So it can be given as E is equal to K times what? What is remaining, which are not constants. These are not constants. So that is flux N. So this is an equation that you are also ought to understand, which relates the generated EMF with a constant of the machine to the useful flux and the speed. That's why they gave us the speed and the useful flux here. It is because of that. So the question is that we need K. So can K be obtained? From this formula, we can simply say K is equal to E over what? If you divide by this, flux N. So it will be phi N, flux N like this. With the same K that we call here. Is the same. If this was there, we're just going to take it from there. But it was limited. So therefore, we are going to use this formula. Because we can see that we have the useful flux, we also have N. So where is E? That's the question, because E is not there. So that's where the generated EMF, that's where this information is playing a role, that we are told it's a series. It's part of a series motor. What they want you there to obtain the generated EMF, which is your back EMF. So you're going to consider to say, all right, it's a series. So how would you calculate this? Remember, in a series, E is equal to what? V minus armature current times the resistance of the armature circuit, which we said we've got RA and RSE. So we ended up with the V into armature current into RA plus RSE of the series. So E was going to be determined. We have got everything there. Remember, your armature current is equal to the what? To the load current we are in series. So let's substitute. That's 300 minus armature current, which is the same because it's there, that is flowing there. It's the same. As the series field is the same. So you're just going to take 36 into what? Armature resistance, 0.25 plus. Remember your generated EMF here, guys. For your diagram complete here, I'm just giving you a sketch. 0.3 for the series field. So you're going to substitute everything, then your generated EMF is there, which is the back EMF. And that was going to give you 280.2 volts. Now, the machine's constant can be determined, which is K, from this generated EMF that we have. The machine's constant can be determined because that was the missing part that we had. So therefore, the machine's constant, all right, that's the machine's constant can be determined, which is equal to E, as we calculated, that gave us 280.2 over what? We have the useful flux, that's 28.75 times 10 to the exponent of minus 3, the milliweber there. So it's 28.75 times 10 to the exponent of minus 3 times what? The speed in revolutions per minute, speed in revs per minute, 980. As it is. So this was going to give you the machine's constant, which was going to be 9.8. That's 9.945 to 3 decimal places. It's a constant, remember. No units. Constant where we do not have the units. So questions can be like that. They want you to relate these equations. And with this information, they can even give you for different, for two conditions where you are given maybe E1 and you're also given N1 and maybe flux. They want you to form, you can even form an equation from that because it will be E1 over E2 is equal to K. This will be flux 1. N1 over K. This will be 2. That will be 2, like this, speed. So at the end, this can cancel and you ended up with this equation, which you can use in your formulations or calculations that you are having later on. So just be geared about that as you move on in your N4, N5, and so on. So this is what we had, guys. Let's just continue to work with more revisions, question papers, as we had questions from the question papers. Try to relate how questions are given and how are you supposed to attempt those typical questions.